Good evening, ma'am.
Good evening, sir.
Make me host. Yeah, thank you. Welcome back. In the previous classes, we learned units and dimensions. In that, we learned fundamental units and all the derivatives for various parameters, various factors. And we also learned precision, accuracy, and we also learned scientific notation, significant figures. Continuation of that, we learned the classification of matter. Now, I learned matter is defined as something which occupies space and has definite mass is called as matter. So matter is defined as something which occupies space and which has definite mass is called as matter. Now, broadly, matter is classified into two. One is physical classification, the other one is chemical classification. And make me a host, man. Okay. So matter is something which occupies space and has definite mass is called as matter. Matter is further classified into two, physical as well as chemical classification. In terms of physical, it is further classified into three, solids, liquids, and gases. Now, for an example, gold is solid. Bromine is liquid. Hydrogen is a gas. Just an example. Now, in case of chemical classification, further they are classified into two, pure substance and impure mixture. Pure substance is further classified into elements and compounds. Now, what is this element? Elements are defined as pure substances made up of same kind of atoms are called as elements. Now, for an example, hydrogen, oxygen, nitrogen, sulfur, all these are called as elements because all these are made up of same kind of atoms. Since hydrogen, H2 is made up of same kind of atoms and O2 is made up of same kind of atoms, N2 is made up of same kind of atoms, and sulfur, S8, is made up of same kind of atoms. All these are called as elements. So elements is as a substance which is made from kind of atoms. Now, compounds, the second classification, compounds, they are formed by combination of atoms of different elements in a definite ratio. Now, for an example, if I take NaCl, NaCl is a compound. Now, sodium is a different type of atom and chlorine is a different type of atom. When they combine in the ratio 1:1, we get the sodium chloride. Sodium chloride is an example for a compound. Likewise, if you take a simple example, H2O, this also can be an example for a compound. 2 hydrogen atom and 1 oxygen atom. Different atoms combining in a definite ratio, and the product which is formed is called as a compound. Now, one more example, if you take NaOH, sodium hydroxide, sodium and OH minus, they are different atoms. They combine to form a compound, NaOH. So, in case of a compound, the elements lose their properties. Now, sodium has a different property, chlorine has a different property. When they combine to form sodium chloride, this sodium chloride will have different properties compared to sodium and also compared to chlorine. They will not have any kind of property with respect to sodium and chloride. The chemical property will be totally different between of sodium chloride. That is what they say. Elements lose their property in the formation during compound formation from their elements. So these elements will lose their property when they form a compound. So compound is formed by chemical composition of atoms of different elements in definite ratio. The properties of compounds are totally different from that of elements from which these are formed. I told you NaCl will have completely different property compared to sodium and chlorine. So compound will have different property compared to the combining elements. And a compound can be organic or inorganic. Compound can be organic or inorganic. NaCl is an inorganic compound. Organic compound, chloromethane, CH3Cl. This will be an example for an organic compound. So organic compound, as we learned, study of carbon and its compounds is called as organic chemistry. We learned that in the first class. So this is with respect to chemical classification. Now, if you see the classification, the chemical classification is broadly into two. One is a pure substance, the other one is impure substance, impure mixtures. This pure substance are classified as elements, compounds. These elements are further classified into metals, non-metals, and metalloids. These elements are further classified into 3: metals, non-metals, and metalloids. Now, example for metal. Gold is an example for metal. Silver is an example for metal. Copper is an example for metal. Non-metals. Carbon is an example for non-metal. Bromine is an example for non-metal. Now, coming to metalloid, a metalloid is element which has both metallic and non-metallic character. Germanium is an example for metalloid. Silicon is an example for metalloid. So elements are classified into 3 further, that is metals, non-metals, and metalloid. Now coming to the mixtures. Mixtures are further classified into 2. One is a homogeneous mixture. The other one is called as heterogeneous mixture. Now for an example, the atmospheric air contains mainly oxygen and nitrogen. Now, these oxygen and nitrogen do not react with each other, but they mix with each other. But this appears as a single component, air. Single, but they have 2 different types of molecules, oxygen and nitrogen. But it appears like a single component. Therefore, they are called as homogeneous mixtures. So homogeneous mixtures means compounds which has same composition throughout the sample is called as homogeneous mixture. If you take air, around 21% will be oxygen and 79% will be nitrogen. So throughout the composition of air is 21% oxygen and 79% nitrogen, around 21% and 79% nitrogen. So therefore, air will be an example for homogeneous mixture. Likewise, alloys. Alloys means mixture of metals. Now, steel is an example for alloy. Brass is an example for alloy. So alloys, they will have different metals in specific composition throughout. Therefore, steel and brass is an example for a homogeneous mixture. It's an alloy. Gasoline, petrol is an example for homogeneous mixture. Even though petrol has different chemical components, it appears like one component. Therefore, gasoline is also an example for a homogeneous mixture. Next, we have heterogeneous mixture. Hetero stands for different, many. So these consist of two or more phases which have different composition. So these consist of two or more phases which have different composition. Example, mixture of sand and salt. Sand is SiO2 and salt is NaCl. They can be differentiated easily. They do not mix with each other to form a homogeneous mixture. They are not uniform throughout. Their composition is not same throughout. So they have, they can be easily differentiated. So they will have different compositions. So those are called as heterogeneous mixture. Heterogeneous mixture consists of two or more phases which have different composition. Now, write the significant figures of the following. These are the exercise which you're supposed to know, supposed to write. Now, what is that significant figure of 1.02? 1.02, the significant figure is 3. 30.9, the significant figure is 3. Zeros in between the non-zero is significant. So all non-zeros are significant. Here it is 4. Here the zero after the digit, zero after the non-zero digit are significant here, which is on the right-hand side. Therefore, the significant figure here is 3. Here the significant figure is 2, because this 0, which is before the non-zero, is not significant. Here the significant figure is 2. So here the significant figure is 4. Here the significant figure is 2. Here the significant figure is 4. So you need to know this to write the significant figures. So I have taught you how to write the significant figures. Now we will write a 0 becomes significant if it comes between two non-zero digits. And you can see here, for a number less than 1, only zeros to the right of the first significant digit are significant. But zeros to the left of the first significant digits are not significant. So here you can see this 0 is not significant. A 0 which is on the left to the non-significant figure, first non-significant figure, is not significant. So this 0 is not significant, but this 0 is significant. Therefore, number of significant figures is 2 here. So here this is between two non-zero. Therefore, this is significant. Here also this is significant. So therefore, the number of significant figures 1.010^3 is 2. Now, the answer of the following problems in standard exponential form. The answer for this in standard exponential form. It is 3.5 to 10 power 13, 3.5 into 10 power 14, 2.15 into 10 to the power 13, or 1.7 into 10 to the power 14. It is 2.0 into 10 to the power 13 plus 1.5 into 10 to the power 14. So the common amongst this is 10 to the power 13. Now I can write this 2.0 into 10 to the power 13, and I can write this as 0.15 into 10 to the power 13. we can write this value as 0.15 10 to the power 13. So in both the cases, 10 to the power 13 is common. So I'll take 10 to the power 13 into 2.0 plus 0.15 is 2.15. 2.15. Therefore, the correct answer for this is 2.15 into 10 power 13. The answer is 2.15 into 10 to the power 13. The next one, division. 24.8 divided by 12.4. The answer is 2. The answer is 2. So the correct answer to this problem in proper number of significant figures. Now for 12.3, the number of significant figure is 3. For 12.4, the number of significant figure is 3. Therefore, the answer should also contain 3 significant figures. So therefore, 2.00 is the correct answer. Next, this is complex multiplication. 152.06 into 0.24, they have given 36.499. The correct answer to this problem in proper number of significant digit. Here the number of significant figure is 5. Here the number of significant figure is 2. 2 is the number of significant figure. So the answer should also be given in 2. You can see 9. It is more than 5. Therefore, we need to add 1. So we can write this as 36.5. 36.5 or 36.5. 36.5. Since it is less than 5, we need to write this number of significant figure in 2 digits. Therefore, we can write it as 36. Hence, the answer for this question is 36, option D. Next question. The correct answer for this problem in proper number of significant digits. 1280 divided by 2. 2.0. That is equal to 1, what's that? No, 0. 640. The answer we'll get is 640. 640. Here the significant figure is 4. Here the significant figure is 2. So the answer should be given in 2 significant figures. Therefore, it will be 6.4. Since 2 decimals, it will be 6.4 into 10 to the power 2. Therefore, the answer will be 640. Say 640. So the answer will be 6.4 into 10 to the power 2. So 2 significant figures. The next question, the correctly reported answer of the addition of 29.4406 and 3.2 and 2.25. The correct reported answer of the addition of 29.4406, 3.2 and 2.25 will have the number of significant figures. So the minimum here is only 2. Here the number of significant figure is 3. Here the significant figure is 2. Here the significant figure is 6. The answer, the final answer should also have only 2 significant figures. Therefore, the answer will be option C. Now coming to some of the other questions. Which one of the following is not an element? Diamond is made of carbon. Graphite is made of carbon. Silica is SiO2. Ozone is made of oxygen. So here silica is a compound because it has 2 different elements, silicon and oxygen. So therefore, the answer for this question is silica. Second question, which one of the following statement is incorrect? All elements are homogeneous. Compounds made up of number of elements are heterogeneous. A mixture is always heterogeneous. Air is a heterogeneous mixture. Which one of the following is incorrect? So all elements are homogeneous, true. Compounds made up of number of elements. Compounds, it clearly says compounds made of number of elements are heterogeneous. A mixture is not always heterogeneous. A mixture can be homogeneous also. Air is an example for homogeneous. Air is a heterogeneous mixture, they say. Air is an example for homogeneous mixture. So therefore, the incorrect statement is option D. Air is heterogeneous mixture. Now, correctly reported answer of the addition of 294.406, 280.208, and 24. The answer will be 416.89 9 and 5, 598.614, 598.614. So this is less than 1, this is less than 5, and this is also less than 5. Therefore, we cannot add, we can retain. So the answer will be 598.6, 598.6, or the minimum, it's 2 here. So it can be summed up to 599. Hence the answer is option B. A mixture that can be separated by sublimation. Sublimation is a process in which solid is directly converted to a gas without going through the solution state. That is called as sublimation. A mixture that can be separated by sublimation. AgCl, NaCl, barium chloride, NaCl, mercurous chloride, NaCl, magnesium chloride, NaCl. Think mercurous chloride and NaCl should be the answer that can be separated by sublimation. Two students, X and Y, report the mass of the same substance as 7.0, 7.0 gram, and 7.00 gram respectively. Which of the following statement is correct? Both are equally accurate. X is more accurate than Y. Y is more accurate than X. Both are inaccurate scientifically. Both are inaccurate scientifically. So both are inaccurate scientifically. If it is 7 grams, we have to just represent as 70 because the number of significant figure is 1. Here the significant figure is 2, and here the significant figure is 3. Therefore, both are scientifically incorrect. Now, coming to the next part of the topic chapter, that is law of chemical combination. Law of chemical combination. The first law is law of conservation of mass. What do you mean by law of conservation of mass? Now, if you a simple example, carbon plus O2, 12 grams of carbon, atomic mass of carbon is 12. A molecular mass of carbon is 32. When 12 grams of carbon is burnt in the presence of oxygen, we get carbon dioxide. It is a gas. The molecular mass of carbon dioxide is 44 here. So if you sum up the mass of the reactants, the mass of the reactants together is 44 grams. And also the product obtained is 44 grams. So this is nothing but law of mass of conservation, or law of conservation of mass. It states that matter is neither created nor destroyed during any physical or chemical change. Matter is neither created nor destroyed. You can see the total mass of the reactant is equal to total mass of the product. Total mass of the reactant before a reaction is equal to total mass of the product after reaction. So chemical combination is a must for the validity of this law. That means chemical has to combine in order to validate this law. What is law of conservation of mass? Matter is neither created nor destroyed during any physical or chemical change. So this is a chemical change. This is an example for chemical change. Now, so during the chemical change, matter is neither created nor destroyed. Here you can see the mass of the reactant before the reaction is 44 and mass of the product after the reaction is also 44. So total mass of the reactants will be equal to total mass of the product. This is called as law of conservation of mass. Now, the second illustration here, when matter undergoes a physical change, a piece of ice is taken in a small conical flask. It is well corked and weighed. The flask is now heated gently to melt the ice solid into water. Now you can see this is a physical process. There's a physical change. So the ice cube is what we take is 100 grams, and it is heated gently so that the ice, water in solid state, melts to form water in the liquid state. That also contains 100 grams of water. Here we have 100 grams of ice cubes. In the second case, after heating gently, we get 100 grams of water. The flask is again weighed. It is found that there is no change in weight, though a physical change has taken place. This is a solid, water in solid state, ice. When we heat it gently, it melts to form water in liquid state. We are taking 100 grams of ice cube, and after heating gently, the ice cube melts and forms 100 grams of water. So before heating, the weight of the ice cubes was 100 grams, and after heating, water which is formed, that also weighs 100 grams. That means there is no change in weight observed, even though physical change is taken place from solid to water. Now, when matter undergoes a chemical change, there's a second, that is physical change, what we spoke about. Chemical change, I gave the example already. So we will take one more example, which is illustrated here. When matter undergoes a chemical change, the following chemical changes illustrate the law. Decomposition of mercuric oxide. Mercuric oxide. Mercury is Hg. If Hg has 2 plus charge, if Hg has plus 2 charge, it is called as mercuric ion. If mercury has plus 1 charge, it is called as mercurous ion. So here, HgO, it is mercuric oxide. This mercuric oxide with 100 grams, we take 100 grams. When heated, this is decomposing to give mercury and half a mole of oxygen. So when heated in a closed tube, it decomposes to produce 92 grams of mercury and 7.4 grams of oxygen gas. So before the reaction, the mass of the mercuric oxide is 100 grams. After the reaction, you can see the sum of the mass is also 100 grams. Thus, in the above decomposition reaction, matter is neither gained or lost. The weight remains the same before the reaction and also after the reaction. This is an illustration for law of conservation of mass, the second chemical process during chemical change. Now, some of the problems based on this. 5.2 grams of calcium carbonate, it is CaCO3, capital O, it is not small o, capital O, calcium carbonate. 5.2 grams of calcium carbonate, then heated produced when heated, produced 1.99 grams of carbon dioxide, and the residue calcium oxide left behind weighs 3.2 grams. Show that these results illustrate law of conservation of mass. Calcium carbonate is CaCO3. When we heat calcium carbonate, it decomposes to form calcium oxide, giving you carbon dioxide. Now, calcium carbonate, calcium atomic mass is 40, carbon atomic mass is 12, and oxygen atomic mass is 16 into 3. So therefore, the total molecular mass of calcium carbonate is 100. So 100 grams of calcium carbonate, when we heat, it gives 56. 40 is the atomic mass of calcium, and 16 is the atomic mass of oxygen. 56 grams of calcium oxide. And carbon dioxide. Carbon dioxide produces 44 grams. So this clearly shows the law of conservation of mass. So before the reaction, the weight of calcium carbonate is 100 grams. And after the reaction, the sum of the mass of the product formed is also 100 grams, 56 plus 44. In the question, they have taken 5.2 grams of calcium carbonate. Now, this 5.2 grams of calcium carbonate, when we heat, clearly they say 1.99 grams of carbon dioxide is formed and 3.2 grams of calcium oxide is formed. So if you add these two, we get 5.19 grams. So initially, before the reaction, it is 5.2 grams we have taken. And after the reaction, the mass observed is 5.19 grams. So the difference in weight is 5.2 minus 5.19, that is equal to 0.01 gram. Now, this 0.01 gram is a very small amount compared to 5.2, 5.19. 0.01 is very less. This is due to experimental errors. Maybe some amount of carbon dioxide would have leaked. Therefore, there is a very, very minor difference. And this experiment also proves that this shows that the law of conservation of mass. The second illustration, when 20 grams of sodium hydrogen carbonate, or it is also called as sodium bicarbonate, sodium hydrogen carbonate or bicarbonate, is heated, 12 grams of, when we heat, we get 12 grams of sodium, 12.62 grams sodium carbonate, 12.62 grams of sodium carbonate, and 5.24 grams of carbon dioxide is produced. How many grams of water is produced? Now, as per the reaction, sodium hydrogen carbonate is 20 grams and 12.6 grams of sodium carbonate is produced and 5.24 grams of carbon dioxide is produced. So what's the mass of water produced? So mass of water produced should be equal to 20 grams of sodium carbonate minus 12.6 grams of 62 grams of sodium bicarbonate, 20 grams of sodium bicarbonate, 12.62 grams of sodium carbonate, and 5.24 grams of carbon dioxide. So that will be equal to 2.14 grams. So the amount of water produced is 2.14 grams. So this reaction also shows the law of conservation of mass. Next is law of definite proportion. Law of constant proportion states that any pure compound, however made, contains the same elements in the fixed ratio of their weight. A pure chemical compound always contains the same elements combined together in the fixed ratio of their weights, whatever its method of preparation may be. Now, this is called as law of constant proportion or law of definite proportion. Now, we will take an illustration given here. Pure water contains 2 grams of hydrogen. Pure water, H2O, contains 2 grams of hydrogen and 16 grams of oxygen. That is, the ratio of hydrogen and oxygen, the ratio of hydrogen and oxygen is 2:16, that is 1:8. 1:8. So the pure water, whether we get it from the river, we get it from the rain, or we get it from tap water, all the water will have hydrogen and oxygen in the ratio 1:8. That is what this law states, law of definite proportion or law of constant proportion. Any pure compound, however made, contains the same elements in the fixed ratio of their weights, the fixed ratio of their weights. So in pure elements, in river water, rainwater, or tap water, the pure elements are hydrogen and oxygen. So the mass of hydrogen is 2 grams and mass of oxygen is 16 grams. So the ratio is always 1:8. This is called as law of definite proportion or law of constant proportion. Now, a few other examples here. A sample of carbon dioxide may be prepared in the laboratory by heating limestone, by burning coal in air, by the action of dilute hydrochloric acid on marble, by heating sodium bicarbonate. In each of these cases, it was found that carbon dioxide is made of same elements, that is carbon and oxygen, combined together in the fixed ratio of 12:32 or 3:8 by mass. 3:8 by mass. Now, carbon dioxide can be prepared by various methods. One is by heating coal. When we burn coal, we get carbon dioxide. The second method is limestone, calcium carbonate. When we heat limestone, this will decompose to form calcium oxide, giving you carbon dioxide. Sodium carbonate, sodium bicarbonate, NaHCO3. I will write here, NaHCO3. When this is allowed to react with HCl, we get Na2CO3, sodium carbonate. So we will get, I'll erase this and write. Sodium carbonate, Na2CO3, when it's allowed to react with HCl, we get 2 moles of sodium chloride, we get 1 mole of water, and we get carbon dioxide. So there are so many methods of preparing, other methods of preparing carbon dioxide here, but we have taken 3 methods here. In all the 3 methods, the atomic mass of carbon is 12 and mass of oxygen is 32. So therefore, here also carbon is 12, oxygen is 32. Here also carbon is 12 and oxygen is 32. So 12:32 is the ratio. Or if you divide this, we can get it as 3:8. Divide by 4, so we get 3:8. So in case of carbon dioxide, the ratio is 3:8. So the law of definite proportion states any pure compound, however made, contains same elements in the fixed ratio of their weights. So pure compound is carbon dioxide. In whatever methods we are preparing carbon dioxide, the combining elements are in fixed ratio. That is, carbon is 12 grams and oxygen is 32 grams. And the ratio is 3:8. Limitations of law of constant composition. It is not applicable if an element exists in different isotopes So it is not applicable if an element exists in different isotopes. So carbon 12, carbon 13, carbon 14, all these are isotopes. Atomic mass varies, atomic number remains same. They are called as isotopes, which may be involved in the formation of the compound. So this law is not applicable if an element exists in different isotopes which may be involved. For example, in the formation of the compound carbon dioxide, carbon-12 isotope combines to give carbon in the ratio 12 is to 32. We learned it. If carbon-14 isotope is combining, so the ratio will be 14 is to 32. Therefore, this law will not be applicable when different isotopes are involved. Isotopes are two laws we learned. What is the first law we learned? We learned the first law as law of conservation of mass. So the amount of the reactants before the reaction will be equal to the amount of product after the reaction, or the mass of the reactant would be equal to the total mass of the product after the reaction. Illustration is given. The next one is law of definite proportion. This law of definite proportion states that any pure compound when formed, however they're prepared, the same elements in the fixed ratio of their weights. So we learned the example of carbon dioxide preparation. Whichever method we prepare, so carbon and oxygen is in the ratio 12 is to 32 in carbon dioxide, or 3 is to 8 in carbon dioxide. And this law is not applicable if the elements exist in different isotopes. So carbon is to oxygen. When carbon 12 is used, it is 12 is to 32. But if we use a different isotope, if we use carbon 14 is to oxygen, there it becomes 14 is to 32. So therefore, when different isotopes are involved, this law of constant proportion is not applicable. Now, one or two problems we will learn. 6.488 grams of lead combines directly with 1.002 grams of oxygen to form lead peroxide. It is also prepared by heating lead nitrate. And it was found that the percentage of oxygen present in lead peroxide is 13.38%. Use this data to illustrate the law of constant composition. Constant composition. To calculate the percentage of oxygen in the first experiment is combination of lead with oxygen. So lead, when heated with oxygen, we get lead peroxide. So mass of lead peroxide formed as per the question is 6.488 grams. Not 6.488 grams, sorry. So mass of lead taken is 6.488 grams. Correct? Mass of lead taken 6.488 grams. And it combines with 1.002 grams of oxygen to form lead peroxide. So the mass of lead peroxide formed during this is 7.490 grams. So this 7.490 grams of lead peroxide contains 1.002 grams of oxygen. Therefore, 100 grams of lead peroxide contains how many grams of oxygen? It is 100 into 1.002 divided by 7.490, that will be equal to 13.38 grams, or we can call it as 13.38%. 13.38%. This is with the reaction between lead and oxygen. The second method, they say, it also can be prepared by heating lead nitrate. Now, in order to compare that, to compare the percentage of oxygen in both the experiments, percentage of oxygen in lead peroxide in the first experiment is 13.38, percentage of oxygen lead peroxide in the second experiment is 13.38. Since the percentage of composition of oxygen in both the samples of lead peroxide is identical, the above data illustrates the constant composition. So clearly they say here, the second case, it's also produced by heating lead nitrate, and it was found that the percentage of oxygen is 13.38. So when lead nitrate is heated, we get lead peroxide plus byproduct. In this lead peroxide, the percentage of oxygen found was to be 13.38. That is the question they've given. That's the question they've given here. When lead nitrate is heated, 38% of oxygen. So even when we prepare lead peroxide by the reaction of lead and oxygen, 13.38% of oxygen is only present. Therefore, this data illustrates the law of constant composition or definite composition. The next problem. Ammonia contains 82.65% nitrogen and 17.65% hydrogen. If law of constant proportion is true, constant composition is true, then the mass of zinc required to give 10 grams of ammonia will be. Then the mass of zinc required to give 10 grams of ammonia. The mass of zinc required to give 10 grams of ammonia will be 40 into 22.65 divided by 100, that is 9.06 grams. The mass of zinc required to give 10 grams of ammonia. Now the next, this problem is not clear for me. We'll work this because this is not clear. The next question, irrespective of the source, pure sample of water always yields 88.89% mass of oxygen and 11.11% mass of hydrogen. This is explained by the law of conservation of mass, constant composition, multiple proportion, constant volume. We never learned multiple proportion nor constant volume till now. It should be either from conservation of mass or constant composition. As in water, hydrogen oxygen is 2/16, or the ratio is 1:8. So oxygen, percentage of oxygen is 8 parts of oxygen divided by total. It's 1 plus 8 into 100. So it is 88.88%. Likewise, percentage of hydrogen is 1 divided by 1 plus 8 into 100. That is equal to 11.11%. Both values are always constant. They obey constant composition. They obey constant composition. And the answer for this question is option B, constant composition. Now, some of the problems we learned, next law is law of multiple proportion. We will learn the law of multiple proportion with an example, and then we will define. Now, hydrogen combines with oxygen to form water. 2 grams of hydrogen combines with 16 grams of oxygen to give 18 grams of water. This is first case. The second case is hydrogen and oxygen gives hydrogen peroxide. So 2 grams of hydrogen combines with 32 grams of oxygen to give 34 grams of hydrogen peroxide. So this is an example for law of multiple proportion. Now, what is this law of multiple proportion? See, the elements here is hydrogen and oxygen. Here also the element is hydrogen and oxygen. When 2 elements combine to form 2 or more compounds. So here the first compound is water. The second compound is hydrogen peroxide, in which fixed weight of one element combines with different weights of other elements will be in simple ratio. Here the ratio is 2:16 or it is 1:8. Here the ratio is 2:32 or it is 1:16. See, when two elements combine, elements is hydrogen and oxygen, to form two or more compounds. Here it's water and here it's hydrogen peroxide, in which one of the weight, in which fixed weight of one element. So here you can see hydrogen, the weight is 2. Here also you can see the weight of hydrogen, what we've taken is 2. So this is fixed. 2 grams of hydrogen combines with the first case 16 grams of oxygen, and the second case 32 grams of oxygen. In the ratio, in the first case it is 1:8, in the second case it is 1:16. This is called as law of multiple proportion. So when two elements combine to form two or more compounds, in which fixed weight of one element, fixed weight, here in this case fixed weight is hydrogen, combines with different weights of oxygen, 16 and 32, will be in simple ratio. Here it's 1:8 and here it's 1:16. Now other example, if you take here, 12 grams of carbon plus half a mole of oxygen gives you carbon monoxide. 12 grams of carbon plus 16 grams of oxygen gives 28 grams of carbon monoxide. Same, carbon plus oxygen gives you carbon dioxide. 12 grams of carbon plus 32 grams of oxygen gives 44 grams of carbon dioxide. So you can see the ratio here is 12:16 and here it is 12:32. So the mass of carbon is fixed. So the fixed mass of carbon, 12 grams, combines with, in the first case, 16 grams of oxygen. In the second case, it combines with 32 grams of oxygen. So therefore, this law is called as law of multiple proportion. Now, what is this law of multiple proportion? When two elements combine to form two or more compounds, in which the fixed weight of one element combines with different weights of other elements, in which is in a simple ratio. Law of multiple proportion. I gave you the example here. They've taken sulfur dioxide, sulfur trioxide. We'll work problems based on law of multiple proportion in the next class. Ma'am, I'll stop.